Good afternoon, guys. I'm not going to wait around for all of this time. We're going to quickly cover down software and then we're going to jump to database for the rest of the guys. So as part of software, we're looking at the section on use case design and we're continuing that. But we're going to now look at how do we identify design elements and then how do we develop a design sequence diagram based on that. Okay. So what you'll see, the transitioning from the analysis classes to design elements is really a matter of that we are moving from what we've discovered during analysis to design, where we're now going to identify different classes based on that. So there's quickly a mention in here about why do we do this. Now they say to us that we must keep in mind that analysis classes only represent conceptual things and this is performing the required behavior. Now the role of this task or step is during identified design elements is where we are now migrating and we're refining our analysis classes to become design elements or design classes. Okay, so these design elements later on is now going to focus on our non-functional requirements. Now non-functional requirements also talks about the performance issues, your design, your security, robustness, all of those. It's not just functions of the system anymore. It is now based on the whole overview of that. Okay, so as we mentioned, this really facilitates the transformation from analysis to design elements or analysis classes. Now where these classes can become a number of things, but it can be broken down in some combination of that. Where a class is going to represent a set of rather fine-grained responsibilities, where that class by itself has a few operations which it's going to perform. Then we can also go down into subsystems to represent a set of coarse-grained responsibilities. Now this subsystem can also be composed of other subsystems, but a subsystem is also composed of actual classes in it. Okay. Now, then you can also have interfaces to represent a abstract declaration of a class or a subsystem to you. Then by making the functionality provided by your class or subsystem available. Okay. So then there's quickly a mention about the difference between classes and subsystems, where your classes fulfill an atomic set of responsibilities and your subsystems are composite building blocks, okay, which are in turn composed of other classes or even other subsystems in our whole bigger picture of the system. Okay, so then there's quickly a mention also about just where we're using stereotypes, and we've spoken about stereotypes in the past, that when we're representing a class, it is going to have a class name, but also a stereotype that groups us or allows us to group typical classes together, classes which perform similar functions. Okay, now the stereotypes which we are looking to be working with is something like this. For example, as we're working with an embedded system, our boundary classes can migrate from becoming buttons. Okay, so a button performs what type of role for a user? It allows the user to interact with the system, as it's an embedded system. Okay. Now, then it also can become, for example, a library. Okay. When would we have a library? When we're working with other actors. What other types of actors do we have? Devices or other systems. Okay. Then the control class can become a normal control class for the use case, or it can become a dispatcher. An entity can become a structure as a struct or a class. We're going to look at it a bit more now. So in overview, what we see is the following. Based on the embedded architecture we discussed, we said our boundary classes is buttons or libraries, for example. Control classes perform the role of control or dispatchers, and entities can either become classes or structures. Okay. Now, how do we identify this? What do we see? Okay, we know that a boundary class can perform the role of what? In analysis, we know that a boundary class can become a form which the user is going to use to interact with the system. That's what we mentioned. But also, because our actors can either become a hardware device or another system. Now, that is where we're looking at. If our user is going to interact with the system, he's going to use some form of a button. Okay. Now, the number of classes can depend on the functionality that is performed, and if it possibly can be generalized into a different structure. Okay. So we can have one boundary class per functionality which is performed. Then a device or another system will provide a library to access that functionality. Okay. So the number of classes also depend on the number of external devices and systems which needs to be interacted with. Okay, so if we are interacting with a motor, we can possibly have a library to allow us to interact with that motor. Okay. So also one library class can be identified for each external device or system. Okay. So then you can mention about the transformation for control classes. So this mapping, what we see, is not always one-to-one. It depends on the required size and complexity of that use case. Okay. So it can go up into more classes, but we'll look at it later on. So other classes may be identified with the application of patterns. For example, if we apply the dispatcher pattern for embedded systems, it adds another class, and this class performs the role of an event coordinator or dispatcher. Okay, where it allows us to do the following. It gives us some lightweight flexibility to accomplish loose coupling between our components, to encapsulate of that coupling, and then also inversion of control between the classes. Okay. So if we're talking about entity classes, what you'll see, it is identified based on the analysis entity classes, and also the mapping is not always one-to-one, as we sometimes might need some form of refactoring or shaping our entity classes and restructuring them a bit. Okay, now these entity classes can be developed as either a structure or struct, or a plain class in C++ to give us that functionality of playing that role. Okay. So as a bit of an overview, that's just saying to us what our classes can become and what is the stereotype going to be quickly for them. Okay. Now, to indicate it and structure it for us a bit, we can go and list them in a short table where we can describe what is the artifact to what this is linked, what this done stereotype is this guy based on, what is the class name, and then also the description to this. So there's quickly a mention where they're saying to us, if we are talking about the artifact, it is the artifact from which you discovered this design class based on what, from where did we get it. Okay. Then the design stereotype refers to the stereotype that is given to that design class, and the class name talks about the actual class name which we'll be using in our diagrams from that point forward. Okay. The description gives us a bit of an overview of what role is that class going to play in our design sequence diagrams when we develop it. Okay. So a completed table can look something like this, where we have our artifacts listed here. Then you can have the design stereotype, the class name, and a brief description of the functionality which they would be performing. Okay. Any questions, guys, so far? Okay, so what you'll see, we are then going to look at using that information to develop a sequence diagram. You've developed sequence diagrams in analysis, but we're going to now look based on our design sequence diagrams. Now, it describes a pattern of interaction among our objects based on chronological order and which sequence did it happen according to some form of time. Okay. So it shows the objects participating in the interaction by the lifelines and the messages that each is possibly sending between them. Okay. Now, it shows the communication behavior between parts of the system, and it can be used to show the behavior specification or a trace of actual runtime communication which we are seeing. So our message which we are discovering can be traced back to the behavior which we can find in the use case specifications. Okay. So in most cases, our sequence diagrams also helps us to expand the use case realizations so that we can identify the classes which builds up this realization to realize a specific use case. Okay, so the realization shows how the objects interact to perform the required behavior in order to perform that requirements use case for us. Okay. So the steps which we will be covering to create a design sequence is firstly to identify the design elements. Then we need to look at the ordering of our design elements or classes, and then we're going to show the interaction between our design elements operations. Okay. So we have, in essence, by creating the table and by discovering your design elements, you've discovered the elements which you're going to have in your class diagram possibly for your use case. Now, what we then need to do is we need to place them in a sequence diagram, where we need to look at the structure and the sequence which they're going to be in. You will still have your primary actor as your first element in your diagram. You will then go and place your user interface elements, the actual buttons or so, which this person is interacting with, as the second lifeline. Then you will have your control classes, which the system is using. That's where the dispatcher is coming in, and the use case controller. Okay. Then we might have our entity classes, which stores some data at that point for us. Then we can also have user interface classes or libraries to communicate with secondary actors. Okay. So in order to determine what is the interactions going to look like and where they are going to be, we need to look and review the special roles and purposes for each of our design elements. So that when you start to look at your use case specification, you're starting to place this. You need to say, if a person is going to interact with the use case, what is he going to use to interact? We can jump back to us. If we have these classes, which of those classes gives us the ability to interact with the system as a user? The button. As the button class contains the attributes and operations related to the requesting of the elevator button. So that allows us as a user to request the elevator. Okay. So, okay. So when we're doing this, we need to look at the purpose of our classes to help us to identify between which lifelines are we communicating. So that when you start to draw your messages in your sequence diagram, you need to keep that in mind. So your use case specification identifies the behavior required to realize a use case, and one or more sequence diagrams may be required to illustrate the object interactions allowing us or needed to perform that use case. Then a typical organization is to have one sequence diagram for the main flow of events and one sequence diagram for your independent subflows or alternative flows beyond that, so that you discover all your operations and messages. Okay. Then there's quickly a mention of the types of messages which we can have. Now, the two types of messages, firstly is synchronous. Now, synchronous is talking about it's a form of bidirectional messages, thing which is used where for us to continue with the next message, we need to firstly have some information that comes back. Okay. Now, we cannot continue with any message after this if we don't get information from this lifeline, if it doesn't pass anything back to us. Okay. Then there's also asynchronous, and this is a one-way type directional message where it is just pushing information without a waiting to continue. Okay. So it can continue based on the rest of this. It doesn't need to wait on any of that. Okay. So what do we need to do when we create a sequence diagram? Okay, we still need our actor. If we had to model quickly that elevator system, we've now identified some classes for it. The classes in this case was the button, there's a floor display library, the control request elevator controller, there's a dispatcher, the elevator, the doors, and the queue. If we have those classes, with which of them are we going to interact firstly? So we are going to interact with the button. So we're requesting an elevator. What happens after that? Then we need to interact with this dispatcher. It plays the role of the main event dispatcher, because the event dispatcher will then allow us to communicate with the request elevate use case. So in terms of that, so the request dispatcher communicates with the controller, and then we might need to interact with the actual queue and to check where is this elevator? Is it coming here? What is it doing? Okay, so that is some information that we might need to add in here. So will this be asynchronous or synchronous communication? Why is it going to be synchronous? Yes, it needs to return back information. What information does it need to return back? Is it coming or has it arrived yet? So it might actually need to come back here. Just make this a bit longer. What else do we need to do? That request elevator also needs to communicate with the queue. But one of the other things that we might need to do is we need to illuminate the button. Okay, so from this guy, there can be a message going backwards. Say illuminate. You can have messages that goes over a lifeline even. Okay. Then we might continue with the rest of the communication. But at this point, we don't have a problem statement. We don't have a use case specification. So we're a bit thumb sucking a bit. Okay. But just to get a perspective, this is what we are seeing. You will also note that I've modeled us as actual classes. Why did we model it as classes? It's now not modeled as stereotypes anymore. It's not like that. Why? Because in design, we're actually moving to classes. Okay. So a lot of our functionality will be performed by classes and objects of classes. Okay. So not as that guy. Okay. Any questions, guys?